So that means, going back to this figure, so z equals 1 corresponds to s equals 0. That's our DC point. And so 1 to the n is a constant, sampled constant unit amplitude. Now, we just looked at z equals j. Z equals j generates a complex sinusoid whose frequency is a quarter of the sampling rate. Now, it is also going in a particular direction. Notice that it was going counterclockwise around the unit circle. And that's this helix right here. If we now go down to minus j, we'll get the opposite sense. It'll hop around the other direction. So it'll go from 1 to minus j, and then to minus 1 and j. So it's actually going the opposite direction around the circle. So we would say this is our positive sampling rate over 4 sinusoid. This is our negative sampling rate over 4 sinusoid. And if you add those together, you'll get a real sinusoid at 1/4 of the sampling rate. And it's interesting, as you approach half the sampling rate, you only get 1 point at z equals minus 1. So is that a positive frequency or negative frequency? What is it? Or is it, I guess it has to be equal amounts of both. But the more you look at it, the more you realize it's degenerate and you don't want it, because it turns out you can't independently specify amplitude and phase there. So that's why this big black line is there to indicate a branch cut. So we actually don't normally even admit things on that line. Now, mathematically, you'll have stuff there, but in practical signal processing, it's good to make sure that there's substantially 0 near half the sampling rate, because your anti-aliasing filter should provide that. So your anti-aliasing filter should start rolling off somewhere around 90% of half the sampling rate. And so there should be a steep filter roll-off here. And by the time you get to half the sampling rate, you should be at minus 100 dB or minus 120 dB. You should be way, way down where you would never hear anything. So you can basically say that there's nothing there that we could hear, and so it doesn't matter whether there's any amplitude or phase control there, because it's all 0. And if it's not 0, go ahead and make it 0. In other words, I've had a lot of nonlinear algorithms develop artifacts there. It's a very common thing to get alternating sequence distortions in your algorithms, especially when they're nonlinear. Stuff just tends to accumulate there, and you know there should never ever be anything there. So it's a really easy way to get rid of some artifacts, to just, after all your processing, go ahead and put a notch there before you go back to the real world, because there shouldn't be anything there. It's a bad place to be for sampled signals. So this is positive frequency. The same thing for negative, so then it will come up. The filter gain will be rolling up, and then the passband probably starts here. And then this is all good stuff. This is all negative frequencies that add to the positive frequencies to give you a real system. And then we get back around to DC. So our j omega axis has become mapped to the unit circle. Why? Because e to the st, if you plug in s equals j omega, becomes e to the j omega capital T, which is modulus 1. So the j omega axis has mapped to the unit circle. And this aliasing is built into the circle. So if you add multiples of the sampling rate, every multiple of the sampling rate you add is just one trip around this circle. So aliasing is built in. It's a very natural representation. And the best feature of this e to the st mapping is that the frequencies are exact up to half the sampling rate, up to, and let's say not including half the sampling rate. In other words, there's no warping of the frequency axis. When we get to the bilinear transform, we'll have a transform that does not alias, and that'll be really great. There's no aliasing, but we'll have warped frequencies as a result. So it'll be linearly mapped for low frequencies. It'll look like e to the st for low frequencies, but then the higher and higher in frequency we go, the more compressive the warping is. And so equal octaves will look like smaller and smaller steps in this unit circle. And half the sampling rate actually is mapped to infinite analog frequency, infinite continuous time frequency. And so that's that's the price of making it not alias. And yet that's what we use more than anything else. The bilinear transform is the most commonly used mapping from the S-plane to the Z-plane. And there are a few others. All right, so that's an introduction to the S-plane and the Z-plane, where the S-plane is where you, it's really the range of the Laplace transforms. There's the domain where the Laplace transform lives after you take it. And then after you take a Z transform, you have a complex function of the Z plane, both of which are just complex planes, but because of the definitions of S and Z, we have these different behaviors for the layout of the frequency axis, the j omega axis in the S plane, and the unit circle in the time in the Z plane. And because of this straight j omega axis in the continuous time case, a lot of filter design is easier in the S plane. A lot of arrangements of poles and zeros turn out to be really simple to work with over the S plane. And when you transform to the Z plane, they become mapped to circles. And so you've got more circle geometry to contend with. And so that is a reason why very often you want to do your design in the S plane. And it's valid for high frequency sampling rates anyway. And then go to the Z plane as an afterthought. All right, so that's S-plane, Z-plane, generalized sine waves. That's what these transforms are made of. And now all we have to understand is how we use them in forming a transform.